Hopefully I'll do a better one here. All right. So given any substance that you want to titrate, A, you must choose the other reactant, B, as something that will react spontaneously with A. Yes? So what two things do you need to keep in mind in order for something to react spontaneously? If I give you an oxidizing agent, what must you choose to react it with? If I give you an oxidizing agent, you must choose to react it with a reducing agent. If I give you a reducing agent, you must choose an oxidizing agent. So you need one thing from both sides of the chart. Yes? In order for the reaction to proceed, what type of reaction should those two substances make? Spontaneous or non-spontaneous? Spontaneous. So do you want the ball to roll up the hill or the ball to roll down the hill? Down the hill. So basically, you just pick a substance B, and then you see, will it go up and down the hill? Mostly these questions are multiple choice. Okay, so it's not like a huge part of the curriculum or anything like that. Before we go into self-indicating let's talk about self-indicating reactants. MnO4. MnO4, when it changes from MnO4 to Mn2+, it actually goes from being purple to being a very pale pink. In fact, it is so pale that it is virtually colorless. So if you make that one of your reactants, it will actually self-indicate. And we'll take a look at an example of that in a moment where we react it with some iron, okay? How would you describe this permanganate ion, given that we have this in the half reaction? Anytime you see that in the half reaction, you need to use the word acidified. If you don't use the word acidified, the answer is wrong, because if you don't have the H there as well, it won't work, okay? And also for this one here, same thing. This is acidified. Dichromate. So we're going to titrate Fe2+. Let's say we were given a list of things and we want to titrate some iron 2+. Iron 2+ is light green. Okay, let's go to our data booklet. So if you could please make sure you've got your data booklet out and on the last page. All right, and let's all find Fe2+ on here. There is one of them right underneath water here. Where are my pens? There are my pens. Okay, so here is an Fe2+. Would it make sense for us to titrate Fe2+ with an oxidizing agent? These guys over here are all oxidizing agents. Would it make sense? Are they? No, reducing agent. Would it make sense for us to titrate it with a reducing agent? I'd like you to look at those substances. Would we titrate it with silver solid or chromium solid? Why would we not titrate Fe2+ with zinc solid? Yes, it is as obvious as it sounds. Because it's a solid, it does not drip well. Yes? Okay, so you cannot use any of, there's no way that you can have Fe2+ react with any of these. And that's what we would need if we had Fe2+ acting as an oxidizing agent. So what that tells me is that probably somewhere here on this table, we have Fe2+ as a reducing agent, and lo and behold, there it is. Yes? And then if we go up to the tippy top of the table, you remember two of those reactants we were looking at were acidified permanganate and acidified dichromate. And you'll notice, where are they on the table? They are right up at the very top, especially the permanganate. So they will react spontaneously with just about everything. Yes, so because they are color changing, so they will act as their own indicator, and because they are so high up on the table, those are very often good choices for substances to titrate something else with, as long as you're trying to titrate a reducing agent. Okay. If you don't have a reducing agent, do we have iodine here somewhere? Yeah, there is iodine. So if anyone taking biology, doing anything with iodine and starch? Anyone done by iodine and starch? What happens with iodine and starch? It turns like a super, super dark blue, almost like black color. And so you can actually use starch as an indicator in this reaction. Okay, so if you needed to react this with something above it, you could. However, let's not worry about that. Right now we're looking and we're saying, what's going to happen if we react the permanganate with the iron? That's going to be a spontaneous reaction. And so we have our pale green Fe2+, we have our dark purple MnO4, and then the pale green Fe2+ turns into a yellow Fe3+. So the solution starts green, and then what happens is you drip in a dark purple and then you swirl it around, and later on you start to get some yellow. Okay, so it will finish yellow. Okay, and once it has gone all from green to yellow, you have hit the equivalence point, yes? However, because it's sort of a pale green and it's not really like a really strong yellow, it's really hard to tell when you've like gotten rid of all the green, right? Because it starts to look yellow and then you're like, when have I gotten rid of all the green? You'll know you've gotten rid of all the iron when your next drop of the dark purple sticks around. Okay? So you're dripping in the dark purple, you swirl it and it turns yellow. You drip in the dark purple, you swirl it, it turns yellow. You drip in the dark purple, et cetera, et cetera, et cetera, et cetera, until finally you drip in the dark purple and instead of turning yellow, it stays purple. Now, unfortunately, you still only have like one drop of purple in a whole mess of yellow. So instead of actually looking purple, it's going to turn a light pinky orange. You are not expected to know that. If you do a lab with this sort of thing, you would be told you're looking for a light pinky orange color. Okay, so at the equivalence point, the next drop of NMNO4 stays purple. Because there's no Fe2 plus to react with. And then we get that light pinky orange color. And if you were to ask me and my friends from high school, we would say that color is porange, because we needed a word that rhymed with orange. And have you ever seen those street lights? Probably not. They don't use them very much anymore. There are certain street lights that are like this pinky orange color, and so we called them porange. And it rhymes with orange. So if you need a rhyme for orange, you can use porange, which is a light pinky orange. Anyway, that's not very useful for you in life. But regardless, to titrate a reducing agent, use an oxidizing agent. Most commonly, you will use that acidified MnO4 because it is so far up the table. It is at the top of the table. And it is self-indicating. If MnO4 is not given as a choice, you can use acidified dichromate. It's not as good because this is orange and this guy is green. So you can imagine, like, you have this green solution and then the next drop of dichromate stays orange. And you're like, what does that look like? Maybe it looks a little bit brownish. You know, it's not a great transition point, but there we are. Okay. Let's see. First of all, check that if you're wanting to titrate an oxidizing agent. So if you're like, I need to titrate silver, or I need to titrate iron, or I need to titrate permanganate, a good choice for those would be iodine, because you can use starch as an indicator. Okay? But you could not use iodine if you had to react it with copper plus or copper 2+, because it simply would not work. Yes? Okay. There are huge quantities of exercises here because it's such a huge part of the curriculum. All right, 2 little exercises there. And with that being said, I'm going to ask you, how did you like the introduction to electrochemistry with Tyler? Did it make sense? Okay, good. How did we feel about galvanic cells? They were all right? Okay, good. So I think today what I'm going to do is I'm just going to give you a few little notes about things. So we're going to go off script just for a moment to work our way into galvanic cells and make sure you do feel 100% about them. So let's say that we had, so if you want some paper, go help yourself. Say we had a beaker and it contained zinc sulfate. And then we had a piece of copper sitting in the zinc sulfate. We have a second beaker and we have copper sulfate. With a piece of zinc sitting in it. And I would like to know which of these two beakers produces a reaction. And I'm going to call somebody's name on this one. So make sure that you are chatting with your neighbor and making sure that you understand what's going on. Do we need a minute more, or are we good to go? Wait. Okay. I can wait. Are we ready? Okay. Baran, which one do you think? Copper 2+ with zinc solid. How do you guys feel about that? We're good? Okay, let's take a look at how we get that, just to make sure we're all on the same page. Okay, so we go to our data booklet and we say, let's get rid of all this nonsense. We have copper 2+ is actually in several places, so let's just find them all. Okay, so we got copper 2+ here, and we've got copper 2+ here, and we have zinc is down here. So yes, that looks good. Yes? Because if I attach those with a line, the ball will roll down the hill. If I were to have done it the other way, if I said I'm going to have zinc 2+ with copper solid, that's not going to work, right? Now, the question is, at this point, which of these two coppers will actually be the one that happens? Am I going to have copper 2+ become copper solid, or am I going to have copper 2+ become copper +1? Okay, so what we're going to use to figure that out is we're going to use these numbers over on the right-hand side, okay? And those values over on the right-hand side are given the symbol E naught. Okay, there's our little naught. And all of these are E naught red. What do you think red stands for? Reduction. So these are all half cell potentials for reduction. So, and it actually says that at the top. They are the reduction potentials of the half cells. Now, if something has a higher potential, is it going to be more spontaneous or less spontaneous? More spontaneous. So if you were to look at my two hills, the one connecting the top copper 2+ with the zinc and the one connecting the bottom one, this is going to have a steeper slope, yes? Yeah? So that's going to be the reaction that occurs. The copper 2+ is going to turn into copper solid, and the zinc, and it's going to react with the zinc going to the zinc 2+. So we're just going to summarize that in that anytime you have a half reaction, the half reaction with the greater half cell potential, the E naught half cell, will be the preferred half reaction, if you have a choice, okay? So let's go back to our other page and write that down. Anytime you have a choice of two half cell reactions, so for example, two reductions, so copper 2+ plus 2 electrons goes to copper solid, and the E naught for the reduction half potential is plus 0.34 volts, or we could have our Cu plus 1 electron goes to copper solid, and that one is at high. Who have we got today? Dylan is here. Thank you. And that one is plus 0.15. You're going to choose the larger half cell potential. In other words, more positive, less negative, half cell reaction, or sorry, half cell potential. So in this case, you would choose this one. Is good? Okay. We're also going to look, these are reductions. So this is a reduction. This is a reduction. Shall we take a look at what we have if we have an oxidation? Okay, and I'm going to give you one where we have two oxidations that both start with the same thing, but I'm going to write them this way. I'm going to write them the same way as they are written on your table. So we have copper plus 1 plus an electron my forward arrow is red because that red for reduction. Yes? My reverse arrow is green because green for oxidation. That doesn't sound as nice as red for reduction, but that's okay. And we get Cu solid. And the E naught for reduction is positive 0.52 volts. Now we also have the reaction that we had up here with the copper 2 plus going to copper solid, Cu2 plus an electron forward. Yeah. I wanted to write this in red. So you can see if you were looking at an oxidation, in this case, the oxidations all go backwards, yes? The oxidations are the reverse reactions. So if we were saying which of these is the preferred oxidation reaction, yes? Yes, thank you. Sorry about that. So it's easy if we're looking at a preferred reduction because our table gives us reduction potentials. But if we're looking for the preferred oxidation, then we need to have the oxidation potential. Can you guess, if we are reversing the reaction, can you guess how we might find the potential of the reverse reaction? It's the easiest possible thing you could think of. Just make it negative. Or if it's negative, you make it positive. It's just like delta H. If you reverse a reaction, the sign changes. Same thing here. And that's actually because delta H is part of what gives these reactions their potential. Okay? There is actually an equation that relates Gibbs free energy, which includes delta H in it, right? Delta G is equal to delta H minus T delta S. So there's an equation that relates the cell potential with Gibbs free energy. So if we want to find the oxidation potential, we just reverse the sign. So it becomes negative 0.52. 2 volts. And this one is negative 0.34 volts. So which of those two oxidations is the preferred oxidation? Cu2 plus. Yeah. Excuse me. Because it is bigger. It's got a bigger potential. It is less negative than the other one. Excuse me. How are we doing for time? We're good. Okay. So if we then go back to here, that means that when we predict our products for this reaction, we are going to have the copper 2 plus is going to become copper solid. It is not going to become, oops, what is wrong with me? Oh, I did not want this one. No, I'm so sorry. I suck. This should have been, okay, back up here. I've written the wrong reaction. Back where we said anytime you have a choice of 2 half reactions, this here should have been copper 2 plus an electron gives copper plus. It is 0.15 volts. I just wrote the wrong reaction, the wrong half reaction. So make sure you change this and this. So out of those 2 reductions, that is our favored reduction for copper 2 plus. Okay. What? Yeah, just 1 electron there. Okay. So are we good with that? So when we predict our products, we are going to predict copper solid as the product, not copper 1 plus, because copper 1 plus is not the preferred reaction. Okay, so this is going to be going to copper solid plus zinc 2 plus. Now this is lovely. You have electrons moving from the zinc to the copper. Yes? Can you get any electricity out of it in this little container here? Can you power a light bulb with this beaker? No. What do you have to do in order to force those electrons to go through a wire? You have to separate the 2 half cells. So you are going to take, and this is where we go back to page, what the heck page was it? This is where we go back to page 69. Not as funny as 67, but still, it's got its own charm, I suppose. You're going to separate your 2 beakers. So you have your zinc over on the left. It doesn't matter. You could put it on the right as well. You got your copper there. You stick a solid piece of zinc into the zinc solution. You stick a solid piece of copper into the copper. So you make sure that you have both the reactant and the product of the half reaction, okay, in the 1 beaker. And this is called our zinc half cell. Again, this is page 69. And this is our copper half cell. And we agreed that was copper going to turn from Cu to Cu2 plus, or was copper going to turn from Cu2 plus to Cu? This is the one that was going to happen, yes? What kind of a half reaction is that? That is reduction. Do you guys remember what we call the stick of metal? That's an electrode. And what do we call the electrode where we have reduction? Do you guys remember that one? That is called the cathode. So the reduction electrode is the cathode. And we're going to leave it there for today. Your homework is going to be 6.3D. Yeah, and then we'll carry on from there. It's on Teams. Yeah. You have winter formal? What time does it end? Okay. We'll think about it. Everyone seems to, yeah. Yeah. Happy New Year.
Yeah, like Dylan. It's a new sentence. Yeah, you saw it in the card? Yeah.
I know, that's like perfect. Hi. I saw you. Oh, yeah. What is that? Oh, it's. Oh my gosh, your nails. It's been so good. Oh, wow. That's so weird. Can I just like go?
Yeah, you want me to show you the cockroach again?
Oh, I need to talk about it. How's what else? Wasn't this your house?
Yeah. Look at me. Look at He's got my phone. Yeah, your phone.
It's not bad. You're like really bad.
Oh,
Can you move? I gotta get that's cute, okay. I'll trash
you keep shopping for him, so.
Guys, why haven't we seen all of this? Hi. Wait, what? Quiz tomorrow? That's from last year.
We're going to get through however much we can get through.
Oh, it's there's a lot of things. Oh, where's the shirt? Why is it so thick?
Pictures. Okay, it's not as scary as it looks. And we're not going to get all the way through it, probably. Yes. Pardon me? I don't know. I would think so.